Welcome, good morning. I hope you had a good night's rest after a very intense first day. It's a real pleasure to have Tim Lenton with us, not only at the Drinks on Sunday and yesterday at Pack House where you rocked it out, but also today as a first keynote speaker. Now, I mentioned Alexander von Humboldt yesterday, who saw, just like the indigenous peoples before him, human society and nature as inseparable parts of a dynamic living whole. And I don't think it's too crazy to draw lineage from Alexander von Humboldt to Tim Lenton via James Lovelock's Gaia theory of a self-regulating Earth, a theory that inspired Tim when he was a teenager to chart his own scientific path and make really fundamental and groundbreaking contributions to our understanding of the natural world. Tim is chair in climate change in Earth system science at Exeter. He's probably most famous for introducing the notion of tipping elements in the climate system, but he's also made wider contributions to Earth system science, writing two wonderful books on the subject, Revolutions That Made the Earth and Earth System Science, a very short introduction. A Renaissance man, just like von Humboldt, Tim not only contributed to the natural sciences, but also the social sciences, working towards identifying positive tipping points to stay within planetary boundaries. He has a book coming out on the subject in September with Oxford University Press, and he's the lead author of the Global Tipping Points report. So without further ado, please join me in welcoming Tim Lenton.
How many people came to the talk last night? Yeah, so I try not to, thank you. I try not to repeat the content from last night, which was a challenge actually, but I tried to stick to the theme, but delve a bit more into particularly, can we anticipate a tipping point before it happens? Because if a bad one's coming, it'd be useful to know. But also if we wanted to trigger those positive tipping points I talked about last night, wouldn't it be great to have a sense of whether the system we're trying to tip or trigger is amenable to that, is close to the tipping point anyway, so it would by definition require less effort to tip the system in the way we want. So I'm going to come to that, but Fabian suggested I should spend a bit of time also talking about the work on giving an update on the tipping points in the climate. So we're going to start the journey there, but I'll start by introducing the concept that there are general signals before you reach a tipping point. Then we'll go into the climate tipping points, and eventually we'll come through to the positive tipping points and see if we can get a forewarning or an early opportunity signal of those. Well, I don't have the chair to do the demo with, but I just put up the movie I used last night. In this case, we're forcing some system with the two alternative stable states, and it's in the one on the left, but we're forcing it in a way that the state that it starts in is losing stability, or what ecologists call resilience, before the tipping point. But the fact that we drew a valley and the ball tended to roll back to the bottom of it is saying that there's some balancing feedback originally in the system that maintains the initial state. But before the tipping point there, where it went kind of abruptly and in a hard to reverse way into the other state, before the tipping point, you saw the valley get shallower, and the ball's being nudged all the time by some variability in the system. But you'll notice that as the valley gets shallower, the ball kind of deviates further from the bottom of the valley and rolls back slower. Does that make sense? And that's because the balancing feedbacks that maintain the old status quo are getting weaker. So there's less restoring force, less strong force bringing the system back to where it originally wanted to be. And that we can pick up some characteristic signals statistically of that slowing response to fluctuations. So this has like a technical name in mathematics and physics, critical slowing down. But we can look at simple statistics, like we expect, if we're measuring the position of the ball, we expect the variance of that position to go up, or the standard deviation, because the ball's going further away from the middle point. But also we use this measure, we talk about autocorrelation in time, but it's simply how similar is the position of the ball from one point of time to the next. And when the whole ball or system slows down, then this measure of autocorrelation in time should go up. So those are two basic measures. We might also, if we were clever, we would realize the shape of the valley is sort of is uneven as we go towards the tipping point, and the position of the ball might sort of skew towards where it's eventually going to tip, and we could look at the skewness of the distribution, or we might look at some other things. Typically we just look at the variance, the autocorrelation, and the autocorrelation was sometimes referred to as AR1, autoregression coefficient. One just means from one time point to the next, because you can measure correlation at different distances. So anyway, what I wanted to show you is some summary of results from different bits of the climate. So this is some data for the extent of the Arctic summer sea ice. This is some data for the altitude of glaciers in the western part of the Greenland ice sheet. This is some data for the strength of the Atlantic overturning circulation. And this is what the variance is doing around the trend line, the red line, in each case. And this is what this autocorrelation measure is doing in each case. And all three of them are showing these characteristic signals consistent with whatever is we call it like the incumbent state of the system is losing some of its resilience or stability. It does not tell you how close the tipping point is. We could discuss how you try and work that out, but it's at least showing that these systems, big, important bits of the climate, are losing stability. By the way, if it works better for you to like stick a hand up and interrupt as we go along, I'm cool with that, whichever way you want to do it. But yeah, there were three systems. I'm sorry, I am not clever enough to work out how to get rid of the thing at the top of Zoom. I thought it was out on the control panel, but it hasn't got rid of it. So if anybody knows which button to press to get rid of the bar at the top, say now.
Maybe you can move it.
Maybe you can move it. I could get rid of me, but I'm not sure how to get rid of this bit. It's more. Try more. Yeah, I like this. This is interactive. Hi.
Floating media.
Legend. Thank you. Whoa. Who was that? You get a prize. Yeah, press escape to show proof. Okay, so this was. Okay, now we rewind 20 years ago, roughly, because it took a while to publish the paper. This was our original map of the tipping elements in the climate system. And there were we were just looking at Arctic sea ice, Atlantic deep water formation or overturning circulation of the Greenland ice sheet. Back then, we'd already also put on the map something that had already happened in my lifetime, and we were trying to repair the ozone hole. But this was our original assessment of which bits of the climate system could pass a tipping point due to human activities. And we always thought that as time went on, some things would come off the map and other things might come on the map. Hence the question marks where we were particularly unsure about stuff. We'll come to an update of the map in a minute, but you see there's quite a lot of tipping elements or bits of the climate system that could be tipped. Right, hold on a sec. Something is now it's got unhappy, possibly because of me. Hold on a second. Well, let's do it that way. All right, showed this one last night, I think. So sorry for the repeat. But so if you weren't there, what this summarizes is that over about the last 20 years, as we've assessed or reassessed how close are the tipping points in a sort of collective sense, which arguably is, as we'll see in a minute, may not be that meaningful a thing to do because we consider them one by one, if you like. But in a collective sense, we used to think it would take 4 or 5 degrees centigrade of global warming before these things became, significant likelihood. Now we think we're already in the danger zone at where we are, roughly 1.3 degrees of warming. Why do we think that? So I thought I'd quickly summarize, what the hell's been going on for the last 15 or so years in climate science that would cause this kind of revision of the risk assessment. Well, we do science and we learn stuff, right? Now, maybe the most powerful source of evidence for most people is the empirical observation. So this is just a sort of simplified summary of some of the observations that have been coming in over the last 20 years or so about the change in some of these crucial tipping elements, showing change in the wrong direction and sometimes accelerating change in the wrong direction, like the Greenland ice sheet experiencing accelerating ice loss, or the West Antarctic ice sheet, or part of it also experiencing that. And in fact, with those two ice sheets, if you ask a glaciologist, they will often say they struggle to rule out whether bits of the Greenland and West Antarctic ice sheet aren't already past a tipping point. You can't sort of say definitively, but in West Antarctica in particular, there's a kind of dynamics which is self-propelling, which may be underway for 2 really important glaciers that drain enough ice sheet that if it collapses, it raises the sea levels of the world about 1.3 meters. If you lose the whole of West Antarctica and the whole of Greenland, you get about 10 meters of sea level rise eventually. The only saving grace is it takes a long time for large ice sheets to be melted. You have to put a lot of heat in. All right, there's a lot of other things on the map, including the Atlantic overturning circulation, which I might briefly come back to because that's the big connector in the climate system and the thing, if it tips, we're all going to know about it. There's also been progress, you might say, in the model world. Now, you might already know that climate models don't include all of these tipping elements. Like a climate modeler usually won't have the ice sheets in the model because there's some timescale separation, we would say. Ice sheets are fairly slow things. We could, as we'll see in a minute, we can model those in what we'd call an offline ice sheet model, force it with the climate model's output. But the climate models do include some of these crucial systems. And what this shows you is in the previous generation of climate models, where there were some abrupt shifts, like tipping point-like behavior going on it's showing you spatially where it happens and in the color scheme of the temperature at which it happens. Something that struck me was a lot of abrupt shifts here at low levels of warming in what's called the subpolar Gaia of the North Atlantic. So a circulation that's got to go anti-clockwise, looping around the bottom of Greenland and kind of brushing up against the Gulf Stream and looping around. In the middle of that loop, the water sinks from the top of the ocean to the bottom. It's one of the two sources of what we call deep convection or deep water in the North Atlantic, there and over here where all these other blobs are. And that forming of deep water is what drives the great overturning as well. You see that there's some models where there are abrupt shifts in the Amazon and lots of Southern Ocean sea ice and so on. The shocking thing, perhaps, was that a lot of the shifts were at low levels of warming in the supposedly state-of-the-art models, showing that the risk is, if you believe the models, the risk is significant. Then here's an example of one of these offline ice sheet simulations. This is from Julius Garber, Ricardo Winkelmann's group. So what we're going to do, or what they're going to do here, is they're going to slowly dial the temperature up, but let the ice sheet equilibrate to whatever the temperature is. Now, it might take 10,000 years for the ice sheet to equilibrate to the temperature. So we're factoring all that time out. We're just saying, if you held the temperature perpetually at whatever level we're at on the x-axis at the bottom, this would be the eventual outcome. So let's have a go. See if I get this to work. It's decided it doesn't like me again. All right, let's try that. Here we go. So now we start to see the first thing that will be the Ross and the ice shelf, and the fish are on the ice shelf. But there, at 2 degrees C of warming, basically we committed the loss of the West Antarctic ice sheet, which is about 3 meters of sea level rise. We're now seeing a thing called Wilkes Basin disappear. That's 3 or 4 meters of sea level rise at around 3 or 4 degrees of warming. And if we were crazy enough to keep warming the planet to about 7 degrees centigrade of global warming, what you're going to see is you start to commit the loss of the East Antarctic ice sheet there, which has about 54 meters of sea level rise, something insane amount. So about 1 billion people live within 10 meters of sea level. I don't know how many live within 70 odd meters of sea level if you lose the whole lot, but a lot of people. So that gives you a sense that, give it enough time, you could tip the loss of the major parts of the Antarctic ice sheet, the 2 major parts. All right, so those are sources of information that we used when we were reviewing, I think it was about 250 studies that had been published on these different tipping elements. And we drew up a couple of maps this time around of the ones where we thought the evidence was strong enough for tipping point behavior. And this first map is the ones where we call them global core tipping elements, because if you tip these, then it's going to have some globally noticeable ramifications. So it could be because of the abrupt breakdown of the permafrost that adds enough carbon and as carbon dioxide and methane to the atmosphere to measurably affect the global temperature. But on here, you've got things like the Great Atlantic Meridional Overturning Circulation, the Amazon, that we might come back to in a minute, and this Labrador Sea or subpolar Gaia convection, and these major ice sheets I was talking about. I just wanted to show you a little bit more about the impacts of some of the tipping points, particularly the yellow ones. because this subpolar gyre thing, most people haven't heard of that. But actually, a tipping point in the subpolar gyre is implicated in what we would call the transition historically from the medieval warm period to the Little Ice Age. And we're here in Amsterdam, so we can all get a picture in our mind of the Dutch masters painting the snowy and icy landscapes of the Netherlands once it switched into the Little Ice Age, and get a sense that the climate that was a very different climate. So if we have a subpolar gyre tipping point again, oh dear, look at that. Sorry, oh my God, this is bad news. Let me try and get rid of that again. Try not to distract myself. Oh no, hide floating meeting controls. Sorry. Right. This is we were just looking at how much would it change the length of the growing season in sort of UK, and we've just about stuck the Netherlands in there. And the effect on the Netherlands doesn't look too bad, but there's like up to a 2-month reduction in the growing season length in major parts of, say, the UK. In fact, what happens is you get a more seasonal climate. You get summer heat waves that could be more severe and persistent, but the winter's suddenly a lot snowier and colder. And that'd be a problem, to put it politely, for UK infrastructure, where we are useless whenever it's too hot or too cold. This is if we lose if the water consistently stops sinking from the top of the ocean to bottom in the Labrador Sea, or what's also called the Omega Seas, which is around the southern tip of Greenland, because this region couples strongly to the atmosphere and then across the Atlantic to where we are. And it's you can think of it in simple terms as being a fundamental shift in sort of a source of heat in some sense, but in circulation as well. Yeah, so I like to think of this as the little brother there's some debate about, in my head, and I think for many oceanographers, they would say, if you lose the deep convection in the Labrador Sea, you have a step down in the strength of the thing called the AMOC, but you still have the deep convection occurring in what's called the Greenland, Iceland, Norwegian seas. So it hasn't stopped entirely, but in most models, it would get weaker. It would go from like 15 spheroids to 10 spheroids for what it's worth, get weaker. And it's also in the models, for what it's worth, it's consistently like a precursor itself of the full AMOC collapse. So we now know that there are 7 models at least, 7 to 9, where the AMOC collapses in the latest generation of models. And in each of those, when you look at it, you see that before it collapses completely, you could say that the early warning sign almost is you'll lose the convection in the Labrador Sea first. That's the work of Steven Drijfhout, who's here at KNMI in the Netherlands. If you want to find out more about that, I'm just telling you, we talk a lot about it, but that's his work. Yeah, right. Hello. Hold a sec. I'm not great on the controls after such a great night last night. Now, if we lose the whole AMOC, I showed last night that it would be a disaster for UK, for global kind of crop production. This was being able to use a more detailed model we had of land use decisions for the UK. So this is some economist colleagues who have enough data from Gregorius, Great Britain's data collection and National Statistics Office to build a skillful model of farmer land use decisions based on climate and all kinds of things. And so, sure enough, in the UK, people, if they can do arable farming, they will, because it's more profitable over here in the east. But with the AMOC tipping point, you basically eliminate arable farming, and everyone's left with grassland and pasture. And you get a sketch of the overall changes. It gets colder on the average, but it also gets a lot drier. And actually, the change in farming would be the least of our worries, because we started calculating how bad is the water deficit for where all the people are here in the southeast. And you've got the winter water supply, but we calculate it's probably not enough to get through the summer on average. So you'd have to have a total change in UK infrastructure, or there'd be a major water security crisis in the UK. Okay, so that's just a hint that these events really matter, and they have big consequences. Then there are some other tipping elements that I think we call them regional impact tipping elements, because the idea is well, maybe you tip these, the whole world doesn't know about it, but a lot of people are going to care. So obviously, if you tipped a collapse of the West African monsoon, that would be like a humanitarian catastrophe for all the people living in the Sahel that depend on the monsoonal rains. The low latitude coral reefs around the tropics, various estimates out there, but they're all in the hundreds of millions for the number of people who depend on low latitude tropical coral reefs for their livelihoods, often for fishing, to support themselves, their families, and maybe to sell, and so on. So we took a look through the literature, as I said, and then we pulled out, we would call these the burning embers, or the kind of uncertain estimates of where the tipping point is for each of the systems. And the ones that are on the first map are in the bold font. So there I decided to call it Subpolar Gyre Labrador Sea. So sorry about the confusing inconsistency of the naming. There's the AMOC and so on. There's Greenland, the West Antarctica. The dotted lines were out like what we assessed was the most likely level of the tipping point. But you can see there's some uncertainty range. There was where we were in warming along the bottom. There was where we're heading later this century, give or take an uncertainty range. If I was doing it again now, in 2025, the yellow would draw down here for the AMOC because a bunch of new studies show it's more vulnerable than we thought it was, and so on. Same for the Amazon, actually. If we were right, let's hope we weren't, then at 1.5 degrees C of warming, we thought at least 4 of these major systems were as likely as not to be tipped. We could be wrong there. Let's hope we're wrong. But you can see if we carry on to like 2.7 degrees of warming later this century, from a risk assessment perspective, it looks awful because you'd be sure you've tipped some things with major consequences. And if you count it up, I think there's like 13 things that might be tipped that would all have these different, quite profound ramifications. I would politely suggest we can't go there because we won't be able to cope in simple terms. We should be doing everything in our power to not go there. Okay. I showed this last night, and that was treating them as independent probabilities. They're not independent. There's coupling. I maybe not won't. If you want me to talk more about the coupling, maybe we do that in the discussion. I touched on it last night, but perhaps the take-home message is you can have situations where tipping one thing makes tipping another less likely. Like if you tip the AMOC first, it's going to cool the North Atlantic region and help protect the Greenland ice sheet from tipping. But if you tip the Greenland ice sheet first, the extra fresh water that comes into the North Atlantic is contributing to the likelihood of tipping the AMOC. Yeah? There's more connections that are in the direction that tipping one thing makes tipping another more likely than connections where tipping one thing makes tipping another less likely. So the way the system is wired up, if you're thinking like an engineer, is not good. It's not catastrophic. I would caution not to too liberally talk about, oh, there could be a cascade of tipping points that's unstoppable. That's actually quite a hard condition to meet, thankfully. I was tempted to say thank God, even though I'm not religious, but there's certainly tipping one thing makes tipping another more likely as the dominant situation. So then let's talk a bit more. Let's revert a bit more to, could we get better early warning information? Can we actually sense the status of tipping elements in the climate? And here's something I flashed up last night, but I'll talk a bit more through what we're up to here. So here's an example where we could use remotely sensed data pertaining to the Amazon rainforest to try to monitor this measure the temporal autocorrelation of fluctuations in the data. But you might be rightly thinking, what is this data measure? I've put VOD. That's not very illuminating, is it? Vegetation optical depth. That also sounds like gobbledygook, doesn't it? So what is this? This is what a remote sensing person would call a passive microwave index. So what does that mean? All right, the Earth is giving off lots of radiation. I think we can all agree on that. Some of it is in the microwave wavelengths. And microwaves interact with water. That's why we use them we make microwave ovens to cook our lunch or whatever. So microwaves are coming off the surface of the Earth, but they may intersect a canopy of rainforest trees with moisture in it. And that moisture may attenuate the microwave signal that is caught by the satellite up above. And it may attenuate it more if there's more moisture in the canopy, or less if there's less. So that kind of makes sense. That's the essence of what this is about. Now we can then debate, oh, what if there's water on the ground, blah, blah, blah. There's some subtleties here. But we were able to show that the vegetation optical depth was a good proxy actually for the biomass of the forest as well. So when the canopy of the forest is bigger, it holds more moisture. And there's a strong correlation. So what we're asserting is this is the best we can do as a proxy for the fluctuating biomass of the forest canopy, which can go up and down. But what we're looking at here is the last 20 years show that the fluctuations that are going on are slowing down, which would be, in crude terms, this measure the system is getting less stable. And actually, each time one of the famous droughts that's happened recently hits the Amazon, we see this spiking of the autocorrelation. We really see also when we look at individual grid cells, we see the forest is struggling to recover. It's taking longer to recover from the hit of the drought. That makes sense, which is a direct sense. It's less resilient than it used to be. On the other hand, if you're watching closely, it gets more stable through the 1990s. So I would say there's probably quite a strong element of internal climate variability here because we know the whole Atlantic region has this multi-decadal variability in the climate to do with fluctuations in the Atlantic overturning. And that could be a key part of the signal, not just any factor of overall warming. But of course, you can say that the droughts that have been hitting the Amazon are unprecedented from what we can deduce from the paleo and instrumental record. So there's definitely also some forcing signal in here. Now, when you summarize it, I've just stopped the movie, but shown you in red the places where the loss of resilience, the increase in this measure AR1 is most consistently positive. In blue are some places where actually we'd say it's getting more resilient. And gray is sort of can't say either way. You already see some structure spatially there. You squint a bit and you'll see probably more red to the south than the north. And we know this is the drier side of the Amazon. It's also the place where the people are doing the most deforestation, although that's scattered around. So we thought we can drill into the data. Let's see if we can find any correlation between this loss of resilience signal and, for example, the rainfall level. So it's a bit complicated, but the colors. Sorry, yeah.
So how can I interpret this? It's like a zero autocorrelation, I can understand.
The negative. Oh, what you mean in a mathematical sense? It would be like if you have the mean trend line, your data. Oh, that you know. The negative autocorrelation is literally, for those that don't know, it's like from one time point to the next, the data might switch from one side of your mean trend line to the other, and on average doing it. But the trend of negative would mean, maybe. So the point is, the absolute value might still be positive, but when we're seeing a negative trend, it's like saying instead of the data slowing down, like we have a long fluctuation or slow recovery, it's actually speeding up. So the system's getting better at recovering from little shocks, is one way of putting it. Which might seem, oh, why would anywhere be getting better? Some of that could happen by chance. So we have to think about this statistically, which is why you're going to see a lot of p-values if you squint at these diagrams. But yeah, essentially some places might be getting more stable, but with the caveat that by chance, you have to consider what could happen, what signal you could get by chance to see if you think what you're looking at is significant. Here we partition the data by annual mean rainfall band, that's the coloring. So the purpley is the driest bits in the sort of baseline climatology of the Amazon, and the yellow is the wettest bits. And you see that, so if the absolute value is higher here, it's saying less resilient, or if it's lower, it's more resilient. And then we can talk about the trend lines. But you can see firstly, in terms of absolute levels of resilience, what can you see, folks? You can see that the dry places are less resilient than the wet places, which is exactly what an ecologist would tell you. In the drier parts of the forest struggle more when they get shocks like droughts or fires or whatever to bounce back, because it's sort of dryness you can think of as the threat to the trees who are trying to maintain the wet climate for themselves and suppress the fires that would otherwise potentially destroy them. But in the trend lines, if you squint, you'll see that the loss of resilience, the gradient is steeper in the drier parts of the forest than in the wetter parts. And these are all reasonably significant, the things I'm saying in terms of the p-values. And this is just a summary plot of the trends, there's not a huge difference in trends, but you certainly see in the very wettest places the trend is less strongly positive. I won't get too hung up on the details. There's a few empty circles. It's not significant. But what we're saying is it's imperfect, but we think we can drill down into the amazing data set we have of remote sensing and start to sense the resilience of really crucial bits of the Earth system, the biosphere and the climate. And sure, we can talk later about the limitations, how can we do it better? But you can also look at the distance to human activities. I'd probably ignore the yellow line, which is places that are furthest from human activities, because if you think about that conceptually, that'll be in the middle of some sort of blobs of the forest surrounded by roads or whatever. And there's very few places that are in the yellow. Sorry.
So the internet currently doesn't see that from end of 90s until like show 2000, you see like the resilience
Lost.
And then
Lost. Sorry, it's being gained when it comes down here. Sorry, I should probably put resilience on the axis here because it would be downwards. So it's gained and then it's lost. It's lost through yeah, I can talk about have we got any data after 2017 because we do. But we had to do the analysis on a consistent data set that we had, and it only went through 2017 at the time. Yeah, this one is just showing you. So these are resilience losses, but basically, if you're nearer to people in the purple, it's already a less resilient part of the forest. That might be just by an association that where the people have gone in and done more deforestation happens to be the drier bits of the Amazon. So you shouldn't maybe overinterpret that. But we can see, arguably, it's subtle, but we can see some of the places nearer human activities were losing resilience more consistently, which is what this is a measure of trend in the data, more consistently than places further from human activities. But the open circles tell you there's maybe not enough data to assert that that's significant. So that one's borderline, but there might be some signal there which would be intuitive, right? Because when humans take the forest away, it doesn't just impact that bit of forest, because the fires and the drying can penetrate in distance into the supposedly intact forest. How far we could discuss. This seems like a long way. We're talking about tens or hundreds of kilometers, but you have to remember that the forest recycles moisture and has a whole range of scales of effect on the climate elsewhere to long length scales. Yeah.
Just in that, like you got
That was a great. I never thought of that. Wow. Okay. Cool. Oh wow. I didn't think of that. Okay. Great. No comment, but I love the idea. Yeah. Interesting. Yeah. That's a very interesting question because we know the absolute rates of deforestation are varying. I have to tell you, I should have told you already that here we're only looking at forest that hasn't been deforested. We're looking at anywhere with greater than 80% tree coverage, which is a sort of standard metric for the intact forest. So we've had to filter out the places that have been eliminated by the end of the data set, which has restricted the data somewhat. All right. Hopefully that was interesting. You're getting a sense of, wow, cool, we could actually do some of this fencing. Yeah.
Just on one previous thing you were mentioning, in terms of the link between those tipping points and climatic points, the report that was done for chat.
Yeah.
If you consider human side of the equation as part of the whole calculation, it seems that the tipping points become a little bit more irregular. But if you consider just biosphere wise, then it's a little bit more predictable. What is the value of that variance?
Great question. You mean? Oh, that's interesting.
The tipping point affects society, and then you have a security problem of any kind.
Yeah. Okay. Very good question. For maybe we return to it in the discussion as well. But yeah, I suppose I'm not sure. I would agree that the tipping points that most immediately, and many of them do, impact human security considerations are going to generate their own feedback loops of how we then respond to that security challenge, which could create their own path dependencies, as we would say in complexity science. And well, great question. I don't think it's one that there's. I think I take your point that then that's something we need to think through. Will be a short summary, because that in turn determines the fate of the couple system, as we were just thinking about for the Amazon. Because this is not a system without human agents in it. Great stuff. All right, I thought I'd talk a bit about could we do better at the early warning or the resilience sensing. This might be, we might skip over this quickly because it's a tiny bit, it's not super technical. I thought I'd leave the maths out. But when we were talking about measuring the variance and the autocorrelation, if mathematically what we'd done is we made an approximation and we fitted the bottom of the valley with a linearization. So effectively, we assumed that you could fit the bottom of the valley with this symmetric quadratic curve, the blue dashed line. But as you see, the actual valley started to sort of change shape in an asymmetric way. If we'd kept in an extra, if we looked at the next term in what in maths we call the Taylor series expansion of what's going on, and we keep the next term in, look at the second order term, we get something like this, which is starting to capture the change in the shape of the valley much better, right? There's then a third order term and a fourth order term and blah, 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 loads of terms. But, you know, when you're doing applied maths, you always make simplifications. So we basically, in the short version, we threw some information out to look at just these two measures, but the data itself would contain extra information about the system and its stability. So we could be smarter and we could like look at the next terms in they're called moments, I think, of the probability distribution and statistics. So I talked about how we could look at skewness. We could look at something called kurtosis, which is sort of, I don't know how to, I don't know, do you know what that is already? But it's like how sort of the relative pointiness versus sort of splurged outness of the distribution, if I could put it in a crude way. But another line of attack is these days is instead of do some harder, do a bit more maths yourself, is train a deep learning or machine learning algorithm to see if it can, in this case, classify that the tipping point is coming or not coming, and potentially classify what sort of tipping point is coming. Because there are tipping points could mathematically take different forms when they're talked about as bifurcations. So without dwelling on the details, Tom Berry and a bunch of us worked together to start to train a deep learning, see if it could spot whether a tipping point was or wasn't coming, and if it could classify whether it was the type I showed you the models of. We'd sometimes call that a fold bifurcation or a saddle node, or whether it could not be a tipping point at all, or whether it could be, well, Hopf bifurcation is we have a system that has it's sort of like we call it a fixed point attractor, like a stable state, but then it tips into an oscillation. Wow, that's funky. Or transcritical, we'd have to draw it on the whiteboard, but it's like we'd say a less catastrophic bifurcation, but we can come back to the details perhaps. Yeah, I won't leap to the whiteboard, but suffice to say, the short version was, well, surprise, surprise, you give the deep learning enough data to train on, so loads of instances of each of these things. You train it up, you go to outer sample testing and throw it with some new information, and it's really good at telling in advance on the bottom row, not only whether a tipping point's coming, but which type it is. It can tell that quite often reliably, many time steps in advance of the tipping point. These are the conventional measures we were looking at before, the autocorrelation and the variance. They behave mathematically differently anyway for the Hopf bifurcation, and there's a different rate of change in the indicators for the transcritical compared to the fold. And clearly the deep learning has learned that in some sense and can tell which thing is coming. And so we could certainly keep training deep learning to do better at this. Of course, we might not know how it's doing better unless it's got this so-called interpretable AI wrapped into it, which don't start asking me questions about that, because I'm like you, probably. I'm one of the people who's trying to understand what's going on in that field and keep up with it, which is quite hard. But I just wanted to show one more thing that Daniel here did, which was you could also train a deep learning to tell if a phase transition is coming in a system. A phase transition is not quite the same thing as a tipping point. I think hopefully we all know what it is in broad terms. Let me skip over the detail, just show you Here's an example of a classic 2D spatial model of a system near a phase transition. This thing is conceptually thought about as something called ferromagnetism, but you could take it more broadly, but it's like the red and the blue. It's lots of little magnets in some, I don't know, iron crystalline material or something like that. Or in the ferromagnetic transition, a couple of different things could happen. You could apply a big magnet and dial up the strength of the big magnetic field. And at some point, all the little magnets are going to tip into alignment with the big magnet. That's a first order phase transition, but that has hysteresis and stuff shown on the right. But interestingly, in a ferromagnet, if you change the temperature, you can reach a critical temperature where all the magnets will kind of collapse into alignment. And that's the second order phase transition. This is the system near the critical temperature where you see that it has spatial structure, it has some order. It's not totally random. There's change in that spatial structure if you're like dialing the temperature towards the critical point. Anyway, Daniel did some cool work where you give not all of the spatial information, but a sort of reduced form of the spatial information to the deep learning. You train it on the different types of phase transition and no phase transitions. And you basically it's skillful at forecasting before the phase transition. And you learn something about how, for example, the spatial data is really informative for the second order phase transition, which would be intuitive, having just seen the spatial structure in the data. So we don't need to get too much into detail, but basically, well, lo and behold, the deep learning can also tell you, we've got a phase transition coming in this system, and it can tell you which type. And that is pertinent because in the climate, you could also have phenomena that have this phase transition type dynamics. And certainly in human social systems, we could discuss that later. Okay, that was a bit about tripping points. It was a bit of the general methods. My plan was now to tip back over to the positive tipping points. Yeah. So we talked about this last night, the conceptual model that, sometimes actions can tip some socio-economic, behavioral, whatever system in principle, and in some empirical cases out of an unsustainable state into a sustainable one. You make the unsustainable state unstable, if that makes sense, and tip into the sustainable state. I wanted to talk about the fact that this does have a theoretical and empirical grounding. It's not just I made this up. There's actually masses of literature with multiple different models for how you can get tipping phenomena in social dynamics. And I'm not pretending that this is a comprehensive summary, and you can read you don't have to squint at the screen, you can read the paper, but I can tell you, you have at least, I put some stuff about ecological systems at the bottom, but above that, there are at least 7 distinct types of mathematically tipping point models for some kind of social dynamics. Often, the tipping point would be conceptualized in the form of what's called a critical mass. So think about this as there's some change in behavior or adoption of technology or something, and the tipping point is defined in terms of a critical mass of a fraction of the population that's adopted, at which one more person adopting triggers everybody else to ultimately adopt, in simple terms. That's a critical mass type tipping point, but it can come about for different reasons. It can happen just in models where we imitate each other with no assumption of rational action or anything like that. That's the purest form of social contagion model. But it can also come about in a rational actor model, something that Brian Arthur, a complexity economist, called the principle of increasing returns. So sometimes if more of us adopt a technology and it gets made more, we get better at making it. So the thing improves in quality and becomes more attractive to adopt. Also, economies of scale. The more we make something, the cheaper it gets to make. And then it's going to be more tempting to adopt. So increasing returns can bring about this critical mass tipping point where the adoption becomes self-propelling, and so on. Don't want you to totally glaze over, just to give you a sense that, okay, wow, there's actually loads of potential tipping phenomena here. Maybe pluralistically, more than one could be going on at once in some of these complex social technological systems. A lot of work to do to get into that, I would say. In each case, the way I like to think is, well, what are the key amplifying feedbacks that will underlie the tipping phenomenon if it exists? Because that's the crucial thing that's always happening at a tipping point. The damping feedbacks that were ruling have kind of lost their power temporarily, if you like, and you've got to spot at the tipping point, some amplifying feedback has got so strong, it can create a change that just carries on by itself. You don't have to keep pushing the system. And that's a very special thing. That doesn't happen in all systems. Maybe I'm deviating from script slightly here, but people often think that positive feedback on its own can give a tipping point, and that's not correct. Positive feedback just describes a situation where you have some change in some, so you've got some feedback loop, you've got A and B and some feedback loop. So you have a 1 unit change in A, and you have some response from B that gives another plus 0.1 unit change in A. That's amplification, that's a positive feedback. But you take that 0.1 unit of change through the feedback loop, you're going to get another 0.01 units of change, which is a bit more amplification. Take it around again, you get 0.001, round and round. That you get amplification, but that converges without completely transforming the system in a self-propelling way. So we call that a constrained amplifying or positive feedback. Tipping points are happening when you've got the situation that 1 unit of change here gives back at least 1 unit of further change from the feedback within the system. Does that make sense? That is the point where, for people who work in systems dynamics, they would talk about, if they're electrical engineers, they'll say something called the gain factor reaches 1. Or if they work in systems dynamics, they'll talk about sometimes the language of runaway feedback, but it's a particularly strong amplifying feedback. It's like a temporary situation, but it's enough to create self-propelling change. Right. Many of these models, well, not all of them, but a lot of work in the field is about, summarized broadly in something called the diffusion of innovation theory. Maybe we don't need to dwell too much on this, but here the conceptual model is you can always partition the population into a distribution. And if it's about the adoption of a technology or a new behavior, there's always going to be some innovators who maybe are the creators of the technology. There'll be some people who are receptive to new things, and there'll be an early adopter. There'll always be some laggards who are like, I never want the electric car or the whatever. But when you have critical mass tipping points, it varies on the context, but often it's somewhere in the range down here. Sometimes it's 25% of the population, sometimes it's just one person that's the critical mass that's enough to ultimately propel everybody else to adopt. And obviously, system by system, we've got to understand something about where is that critical mass tipping point. In the case of the Norwegian car sales that I showed last night, my assessment, having looked at the data, is that the tipping point was fairly early on. If you thought of it in terms of in 2012, 13 or thereabouts, depending on where you were in Norway, because of the policy incentives in place, if you thought about what's the total cost of ownership for me if I get an electric car versus a petrol or diesel one, the electric car was cost competitive, or the total cost of ownership was equal for an electric car as a petrol or diesel one very early in Norway. And at that point, you're really in this exponential up curve of adoption there. So arguably the tipping point was at pretty low levels of total adoption, but was consistent with it being kind of an economically rational choice. In a less well-off country, say China, the evidence that I've looked at would suggest the tipping point is closer to where what we call the sticker price or the purchase price is equivalent for electric versus a petrol or diesel car. So these things can change with context. But where I wanted to go here was not into that, but more into, well, Norway tipped, but could we tell whether a tipping point is coming in something like the car market towards electric cars for a place where it hasn't happened yet? So let's hypothesize that just like the Amazon rainforest or the complex bits of the climate, there might be signals in the marketplace, which I'm going to call early opportunity signals, that a market is more amenable to tipping to the new technology than the old one. So be looking for the same signal that there'll be fluctuations going on in the system anyway. We look to see if they're getting larger and the recovery is slowing down. Does that make some kind of sense? So we just thought, I just thought, well, let's give it a go. There was loads of people who would say, this is never going to work. There's loads of people who'll say, oh, we're, marketplace, all these intelligent human agents who are just going to keep adjusting their behavior in response to whatever they see going on. And that makes it, you can't treat it in the same way, blah, blah, blah. But it's an empirical question. Does it work or doesn't it? So first of all, we started playing about. We were like, so you got the conceptual model of resilience, fast recovery, high resilience, slow recovery, low resilience. We talked about this. We thought, oh, well, there was a big disruption in the car market when the financial crash happened in 2008-9. How did recovery look in different geographies? In Germany, there was loads of subsidy support for the German car industry because it's like the core of their economy. And it doesn't take much of a hit, the sales of the internal combustion engine vehicle. In a country like Denmark, yeah, the crisis caused a hit in sales, but a relatively quick recovery. In the USA, it seems the market was less resilient in the sense that it took a hit in sales, it took longer to recover, and we could pick. And in Greece, where the whole economy was going kaput, it never really recovered. So already, oh, right, there is differences in different marketplaces. That's interesting. So then we switched to our challenge of tipping away from internal combustion engine vehicles. So we summed up some data for the three biggest car markets in Europe. We took the Chinese data, the US data. So it's the market share of the petrol and diesel cars. We cut the data before the pandemic starts when all sorts of stuff goes on. We're including a precipitous drop, or you might say a tipping point change in the sales of the conventional technology in the European market, the Chinese market, but arguably not the US market. Well, you can't really see them, but there are fluctuations in the data here in each of these things. So let's blow up what fluctuations look like for the dotted line. And lo and behold, their variance goes up and the fluctuations slow down. I don't have to do statistics to convince you of that, I hope. You can just look at this data. You can see the variability is way bigger there than it is there. You can see that fluctuations are longer lived here than they are here. So there is slowing down in the fluctuations of the market share of the conventional cars in the European market and also very clearly in the Chinese market before you really see arguably any strong signal in the actual absolute market share sales or whatever. But in the US, there's no consistent signal and it doesn't tank in the same way. Well, that feels like informative. I mean, it's useful information. If you were a policymaker who was beforehand thinking, I've been doing all this work, I want to tip the market to EVs, but is the market ready to tip or not? We actually retrospectively were saying there was information there that would tell you you keep working at it, policymaker, because it's near to the tipping point in these geographies. But if you're in the US, I'm afraid you're going to have to work harder because we're not seeing the evidence that it's ready to tip. That's not published yet, but we're sort of revising the paper. But we have managed to publish something looking at some other data. Slightly different thing. We're looking at advert view shares on the UK's leading website where people buy and sell their cars. So it's mostly the second-hand market, although increasingly now, new cars can also be sold there. So what is looking at an advert? It's not the same thing as buying a car, but it's showing interest in the alternative technology. And here we're looking at the share of all advert views. That's people looking at electric vehicle adverts. And there's a general upward trend. Okay, people are getting more interested in the new technology. There are some big spikes. These are to do with this one was the government announcing a ban on petrol and diesel car sales in 2035. This was the government announcing that it was going to bring that ban forward to 2030. This was a fuel price spike. So was this and this, and I can't remember which one was which. But that's causing the spikes. But you can just immediately see by eye that the rate of decay back to you might say the norm, which is mostly people are just looking at the petrol and diesel cars, it was pretty fast back here, but over here it was a much slower decay in response to the perturbation. So you could say that the incumbent thing, which is to be mostly everyone's looking at petrol or diesel cars, is getting less resilient, and the interest in electric vehicles is getting more resilient in some broad sense.
That's the recent sort of tinkering with the UK government policy on date phase and have much of an impact.
That's a great question. We haven't seen that yet in the data, which here you can see was through quite a bit of 2023, but we do have more recent data, so I might go back and try and answer that for you. But what we did the basic analysis to show, I mean, you can measure the recovery rate from the big spikes and see it takes longer. You can run the other indicators we talked about, and lo and behold, they go up. But that was also visible. The variance is obviously bigger here than it is here. Maybe it's not so obvious that the fluctuations are longer lived there, the little fluctuations, but they are. But yeah.
It's interesting, the government, they think these are big political moments.
Yeah.
Perhaps
the way to think about it, the way to think about this is a beautiful complex system with all this feedback in the system. Like, who's to say? I know we may not have identified all the feedbacks, but there's many. What I'm showing on this graph, for example, is the more on the dotted lines, the more there's adoption of electric vehicles, the cheaper the batteries get, and therefore the vehicles get. They plummeted, the batteries plummeted in price over a decade, economies of scale, you could say, but the batteries got better as well. The range you could get from a given mass of battery went up nearly a factor of 3 in a decade, that's impressive. That's pretty amazing to anybody who's sort of vaguely technologically interested. So that's real increasing returns, right? It's now a way more attractive proposition, the technology, than it was. It's cheaper and it's way better. And sure enough, you've got this exponential growth. This is the global stock of the fleet of electric vehicles. It's doubling. At this point, it's doubling every year and a half, and it's still doing so, actually. And there's a little Ukraine war happens, and there's a little blip in the decline in the battery prices. But if I showed you the data 2023 and the estimate for 2024, the battery prices continued to plummet. There's all sorts of craziness, as we could all discuss, going on in global trade and blah, blah, blah. But in raw kind of evolution of the technology, the feedback continues. So what I wanted to do is not just to wrap up, perhaps, is not just talk about this idea of, we might get some early opportunity signals. What I wanted to finish up on is, hey, we know something about these feedbacks, right? I'm showing you some data. Like I can quantify the learning rate, as it's called, for battery technology. You know, how much, for example, how I can quantify how much cheaper batteries are going to get if we double the number of batteries we made, and so on. And my colleagues, not me, but Jean-Francois Mercure, Femke Neisser and others, lead the development of a model that's a model of competing technologies. In this case, it could be the internal combustion engine and battery electric cars, or hydrogen fuel cell cars, or whatever. Without getting too much into the details, it's well appreciated in this field of technology transitions that a good mathematical representation of like tipping from one technology to another is something that to ecologists they would call Lotka-Volterra mathematical description of how species compete. Conceptually, in this case, you might say, let's say, the two types of technology are fundamentally different species in an ecological sense. But within a given species, there are different individuals, which might be the different firms conceptually making different instances of electric vehicles. The maths is actually kind of equivalent. And already we know, because mathematicians have been at it for a while, the type of tipping dynamics that you could have in this general mathematics. Sometimes it's the really abrupt tipping I talked about. Sometimes it's like you could tip into coexistence of technologies. This depends on how strong the competition is between like the two species, the two technologies. But we know stuff about this. Basically, we can build a principled model where the crucial things that we need to be able to, from data, say something about how strong are the crucial feedbacks, but we've got some data and we've got it from different markets, so we can do that. And how strong is the competition? We've also got some information on that. So what Jean-Paul Sarmakura started and others continue is making models that are calibrated on real data for and effectively give you answers embedded in a model of how close are different markets to representation to the tipping point, maybe defined a little bit indirectly in terms of, say, here I'm showing you plots of where do you reach do you reach the point of price parity in terms of, I think, find total cost of ownership in this case. In different markets like EU, US, China, India. And the answer is, like, we were already saying we were very close anyway in China, and that's proven to be the case. Not far away in Europe, a bit further away in the US, could be close in India. The other thing that goes on, once you've built a model like this, is you can actually play with the model and you can say, how effective would this policy or that policy be? Not just if it was imposed in a specific market, but because this is a model of these coupled markets, what effect does it have on the other markets? So the policy we're really interested in that I mentioned last night is mandates, they're called. It's like, we talked about it. It's like, oh, you are not going to be able to sell petrol or diesel cars in our market after date X, 2035, whatever. That you couldn't come up with a better impetus for car manufacturers to be forced into retooling their production lines because they know they won't be able to sell any product if they aren't making the new product. And so that's a really effective policy to get them over the hump of shit, it's going to cost a lot to like put in the different production lines. I'm resisting doing that. But then again, if I do it, I can really win big in with the new demand market. So mandates are really effective to stimulate all the feedbacks I was talking about before, which is we learn that, we're going to get better and better at making these batteries and these electric cars. They're going to get cheaper and better, and then that's going to get us more sales and blah, blah, blah. So yeah, the mandates work, but they don't just work in the market you put them in, the bans. You kind of, let's take Europe. If Europe bans the sale of the internal combustion engine vehicles, it stimulates innovation, might bring the tipping point forward by like a year. But there are bigger markets out there like the US and China. If they also ban, it has an impact in our market because this is a globalized marketplace. The batteries are traded around the world. Well, I was thinking pre-Trump here, right? But so there's a few caveats, but we all benefit from the innovation wherever it's happening. And that really matters for some countries. You could really bring forward that tipping point, not just for yourself, but for other people through this policy action. And the policy, obviously, if it were coordinated, it would make sense, but it doesn't have to be coordinated to get these knock-on benefits elsewhere. It's just the way things are in the complex system. And this crew have also been, we showed this last night, they're also modeling out the electricity power sector with all the information we have about how, like, the solar panels here get cheaper the more we deploy them. We know about how the learning rate, as it's called, for wind power. We know about the learning rate for a bunch of technologies. So that was how Femke could make a principled model which would answer a question about what's the cheapest form of electricity in any given country if you factor in the storage you need for renewable electricity as we go into the future. So I showed this last night, and basically, because solar is getting cheaper faster than anything else, or the learning curve is better in solar, that's why solar is projected to dominate. Great. And I flashed past this, but we just started working a year ago, and we're just about to submit the paper on. We found enough data to calibrate how there are some interactions between the sectors of the economy, like batteries are coming out of second-hand out of EVs at end of life, and they can go onto the grid and be used for grid electricity storage. And that can really decrease the price of grid electricity storage because there's a whole load of batteries coming out of the power sector, and so on. Well, anyway, I didn't dwell on it last night, but we modeled all of that out. We looked at the effect of different kinds of policy, including the phase-out mandates for the power sector, for heating or cooling our homes, so going to heat pumps, for personal mobility like two-wheelers, three-wheelers, cars, electrifying, and for goods transport on the roads, for trucking. And the green wedges are like the clean technology here, or the yellow and blue there. Basically, the mandates are way the most effective for sectors that that maybe like trucking are further away from the tipping point. And when you're in the power sector, you're close to the tipping point anyway. You can have, the relative effectiveness of different policies like carbon taxes or subsidies can be greater. There's a load of learning that's going on about this, but we're getting into a place where we can say useful things in a sort of data informed way about which are the most effective policies to bring forward the positive tipping points that hopefully we agree that we need. Right, skip over that. Because you can't build a model of the stuff. You can't build a very good model of the stuff that needs to happen, but is hardly happening yet, which is like the green hydrogen economy. So you resort to drawing like spaghetti like this, which is a sort of simple diagram of how you could have reinforcing feedback cascade to a green hydrogen economy. And you can make a few crude calculations about, you can estimate the learning rate for green hydrogen. This is using renewable energy to split water to get the hydrogen that you can use as the basis to make synthetic fuels, or to reduce iron to make steel in a clean way, and blah, blah, blah. We've got some information on the fact that there's a really impressive learning rate there. You use a thing called an electrolyzer to split water, but the evidence already shows that you make bigger and more electrolyzers and they decline in price considerably, the green hydrogen manufacture. But at that point, you can only do what you can do with limited data. Suffice to say, you can make a case that you could have a cascade of tipping, if you like, or reinforcing feedback in the transition to this alternative state of the energy system. Enough from me. Thanks a lot. Read all about it from the 11th of September if you're interested. Yeah.
Thank you very much, Tim, for this tour de force. We have around 20 minutes or so for questions. Please raise your hand here. The idea in the front.
Yeah, thank you so much. I have two questions. The first one is related to, you were talking about calculating tipping points and conflict tipping points, and how one tipping point made other tipping points more or less likely. I was wondering if you've also noticed that
I think historically, I'm not. You tell me if this is a good way to describe it, but if you think of universal suffrage or votes for women in particular, that's an example where it happens first in some geographies but spreads to others. If you think about equal marriage, even just within the US, but look at decisions made by individual states, and you look at the data of that, you'll actually see there's a lot of kind of cascading dynamics, sometimes in a good direction, sometimes in a bad. So in the social system, it is clear that there's learning going on between cultures or geographies. So you might reasonably choose to describe that as the tipping cascading through the wider social system. There's probably other ways of describing it. You could just call it diffusion. But yeah, I think that's a useful way of thinking, particularly for those fundamental shifts in social norms. And I'm trying to make the case that for some of these really important technologies, you can describe it or think about it that way, because by tipping, even little Norway, which is like a tiny car market, maybe it's not strong enough to trigger the next tipping point, but it very, very clearly signaled to a lot of car manufacturers in other countries that this is possible, and encourage some policymakers to deploy similar policies, because socially we're always like looking at what each other are doing and learning from that. So in that sense, even if we will depend on how we define a cascade, whether we describe it as a true cascade. A purist might say it's only a cascade if tipping one thing makes tipping another inevitable. That's a very restrictive condition. But if we just define it as tipping one thing makes tipping another more likely, then that's certainly the case.
Angelique?
Yeah, thank you very much for that. the most positive class.
Yeah.
Tipping points like volatility, prices,
Mm-hmm.
one needs to show better returns. I'm also thinking about this in the context of like very far right government.
Yeah. Yeah.
What for you then is positive.
Yeah, that's a great question because that's like when we use positive in that normative sense, it's almost like an ethical question, or I have to be clear of what I mean by positive or positive for whom. So I ended up touching on this. We touched on this in the questions last night. So the first thing I want to say is, I know this is crude, but if you imagine the scales of justice, and you accept that on one side of the scales of justice are people already suffering direct harm from climate change. How many people are they? How bad's the harm? Well, the actual death toll right now, people would debate the numbers. Is it in the thousands, in the millions? But I've done work myself to show that the number of people who are going to suffer harm and risk of fatality escalates very significantly, and as we carry on with the inertia in the climate to higher levels of warming. So in simple terms, there are hundreds of millions of people on one side of the scale of justice, possibly billions already. We want to alleviate that harm or that projected harm, or I do. For me, that's a hell of a lot of harm that I'm trying to alleviate. And so everything, the most positive thing in that sense, and we'll come to some other nuances in a minute, is what's most effective at stopping fossil fuel burning and greenhouse gas emissions to alleviate the otherwise intolerable harm over here. Well, for that, you need to know something about which activities contribute the most to net emissions, cumulative. The power sector, about a quarter, so that's a big area. That's what we eat, too much meat in simple terms, about a quarter. Equally important, I'd say, very different dynamics. The road transport, about 12, 13% on the global average, so maybe half as important as the power sector, but still very important, and so on. And then positive, you've also got to factor in, well, we don't want to create gratuitous new harms for people by tipping technology. But you've also got to think about the benefits you're creating in the new technology for people. So people, as we heard last night, everybody goes, oh, but what about the lithium mine in Chile, or what about the cobalt miners in the Democratic Republic of Congo? There's those, we need to avoid gratuitously creating localized harms. But we also need to remember, hold on a minute, in the case of electric vehicles, clean air, how many people die from fossil fuel air pollution every year in the world, folks, roughly, do you think?
8 million.
Yeah, well done. You know the answer. That's a lot of people. That's a harm, and a lot of that, some of it is still dirty coal burning. Quite a lot of it is road transport pollution. We're going to alleviate that harm. They were also on this side of the scales of justice. Oh, and then think about, so a great question because it opens up this thinking. Then think about, I told you last night, 80% of people live in net fossil fuel importing countries. So that's for our balance, our net economic balance, we're paying, that's a cost. Renewable energy is very widely distributed, and some of the best sources are in some of the poorest countries. So if those countries own the source of their own energy, it's immediately a massive benefit on their country balance sheet. So that's a huge co-benefit. Let's not carry on going through all of this stuff, but how I determine what's positive is by trying to get the numbers on those different things and weigh them up. And for me, there's no contest. I don't want, the lithium, the cobalt miners to be unnecessarily suffering. But any moral philosophical question requires weighing up relative harms and blah, blah, blah. And wow, the benefits here are spectacular.
Yeah.
Good. Great, great. Yeah, I'm glad you asked that because I didn't give you some examples I enjoyed writing about in the book of tipping points that considerably reduce demand. One of my favorites, who's heard of Cool Biz Fashion in Japan? You have, yeah. Good. Well, that is a lovely national scale example, which maybe I won't spoil for you. But there was a kind of social tipping, norm tipping in dress codes that meant you could save a lot of energy by not setting the air conditioning temperature set point so low in buildings because people had changed their dress code to be more comfortable at 28 degrees C rather than 22. Da, 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 da. That's a significant demand reduction, sort of social behavioral tipping that we could learn something from. I've got a few other examples. I think that this is an area we should be looking at more because I totally agree with you that often the most effective thing to do is reduce demand. What I will note is I wouldn't conceptually totally separate notions of efficiency from notions of reducing demand. Why do I say that? Because in the energy system, one needs to think about the final end use of energy. And if you take a case like, I don't know, heating or cooling your home, you radically reduce the demand for the original energy demand to achieve that final service if you electrify the process of heating or cooling your home, if that makes any sense. So they're not, I wouldn't conceptually totally separate them because you've got to think in terms of reducing the final demand, that is a function of technology choices. But yeah, I love the question because we could all do more work on, like I also look into flight shaming in Sweden that really took off. I thought that was really, really interesting. And I see other instances of those kind of movements. And I think that that's also places where I think around eating meat, it could be the crucial one, basically. Could we imagine a world where you're in the restaurant and you see somebody order a steak and everybody looks across like, what the hell are they doing? Just like when if I'm old enough to remember you'd be in a restaurant and people would be smoking. That was the norm. Now, if somebody lit up in the restaurant, you'd all be going like, who the fuck is that? Get out of here. Pardon my French. So could that happen for me? Oh, it's a slightly different thing. It's not directly, you're not having to inhale the smoke of the beef, but you kind of know it's harming you. Their choice. So yeah, enough said.
So I want to ask you something more technical. I wanted to ask, since you did the indexes about vegetation, I was wondering what the indexes to use, what worked out, and if you think that there is some safe baseline of resilience value that works before the tipping point happens anyway. Like if there is some good index to maintain, when we talk about restoration projects.
Brilliant. Oh, drop me an email to maybe carry on the conversation with the group because we're doing great questions. Work in progress, I reckon. In terms of just on the early question about indices we looked at, we have been looking across, there's this very famous NDVI index, it's called, for greenness. There's now KNDVI, which is trying to sort of capture some of the variance in what would otherwise be sort of you wouldn't see it in the original index. And then there's EVI, and then there's how many other indices. We've been having a look at all of them, and my colleague Nicholas Bohr's group has probably been having a look at all of them in more depth. And somebody called Wanda de Keersmacher, who has written some really brilliant papers on this, who works actually came out of Wageningen here in the Netherlands. So yeah, there's groups of people doing exactly that work and trying to answer those questions. But I think it's probably fair to say it's a community effort to keep kind of coming to some sensible consensus on what's the best indices, the best metrics, the best ways to measure these things. Yeah. Yeah.
It's very energy. I mean, it's expensive. Right?
Yeah. So one thing we've been doing is you have to you always want to ground truth your like satellite based thing. So Kirsten Lees, who spent a bit of time in my group, she's a faculty member, University of Derby in the UK. Her passion is peatlands. We were doing stuff on how ground synthetic aperture radar penetrates the ground in like a upland peatland that bounces off the water table. We're able to show with the places where there are actually people drill cores in the ground that it was measuring the actual water table, not something else. But we could look at or Kirsten could look at the resilience of the water table to being lowered by a drought. How quickly would it bounce back? You could map that spatially in beautiful detail. But there'd be loads of other stuff like that that's possible. It just needs people to get brainstorming and creative and think about, oh, what could we do? Let's try it. I'm convinced that we're sat on a massive information that we've not extracted yet, that's useful to work on. I mean, that's an easy win as a scientist if you can find new insight and information in what's out there. Right.
Hey. As we focus a lot in technology, I was wondering, do you think that we can have absolute gigabits on economic growth?
Ah, that old test up. Well, I did focus quite a bit on technology, although probably last night I emphasized more the social dynamics. I wouldn't want to privilege too much one thing over the other. I think the questions are brilliant around, hold on a minute, what about reducing demand? Because that is super effective. And I never felt comfortable in this kind of neoliberal consumerist culture since I was a kid. I felt deeply uncomfortable. So something's not right for me. I'm comfortable with leading a more frugal life. I'm not saying it's super frugal, but so on your specific question, this, in my honest view, is that at some point we obviously have to abandon the idea of indefinite economic growth. That's been clearly and coherently argued by ecological economists for well over half a century, and there's no contesting it in my view. However, we need to think practically about what we need to do now, and in transforming the energy system, every decent model will tell you because it will create better jobs. It already is creating better jobs, and in that sense, it's also creating often more productive jobs, as an economist would define it. So there's going to be some, you could say, well, let's at least call it gain in productivity or something you might crudely call growth, just in the business of making a whole new energy system. How much of that system we need to make? We'd rather make less than more, because it's meaningless to be making on the assumption of indefinite growth. But still, from what we've modeled out, in this transition, there's one set of dynamics to consider. As for specifically on decoupling, well, the evidence, even when you consider the offshoring of emissions by a country like the UK, you find instances of countries, maybe only about 7 of them at the moment, where absolute decoupling with regard to greenhouse gas emissions, I would say, is occurring in the data. And our world in data would say the same thing. I don't know if Julia Steinberger, if she was here, would disagree with me or not on that. It's more about, it could be more about rate, etc. I find it heartening that we are achieving absolute decoupling in my highly flawed neoliberal country, the UK. That tells me something, because you could definitely do better than the UK, and yet somehow we're managing it. I believe we've reduced our total energy demand per capita by something like 20 to 25% in as many years, and nobody's noticed, if I'm frank with you. So I see some glimmers of hope, but I would still be with the questioners in saying we should be looking very hard at the tipping points and norms that are going to lower demand. They're just going to be really powerful. Yeah, and then I'd say I think we're going to go on the journey to having to redefine the notions of progress and what counts as an achievement as a society, and abandon GDP as a sort of flawed and measure. But I would not advise going straight for that, weirdly, because I would have done 20 years ago, and I tried to, but we got nowhere. If you, in Donella Meadows' framework of leverage points and systems thinking, and my learning as a systems thinker, although we know what the most powerful leverage points are, and they will be to change the paradigm, and I talked about that last night, strategically, I think the lesson of history and recent history is you don't always get anywhere if you go straight for the ultimately most powerful tipping point. I might be wrong on this, but my observation is we open the space and we start creating changes that then make it easier and more necessary to challenge and to create these deeper changes. I could be wrong on that. I'm happy for us to take different views, but that seems to be, if you've got to remember you're in the incumbent state of the system, so you have to be able to do something that the incumbent state stakeholders or whoever participants in, enough of them are sort of on board with it. And that's the subtlety in the argument here, that if you come in through the lens of the argument I've been making, I can get the financial sector and other people who we might think of as our enemies on board and becoming part of the change. Later on, they might find themselves in territory that seems a bit crazy because they're going to be undermining the core paradigm that their businesses run on. But I think I'm not saying it's the best strategy, but it's strategically thinking, it seems to have some traction. But maybe that feels, to an idealist, that won't feel perfect. If we're in our idealist selves, we'd rather, smash the system, let's erect a whole new system that's not built on these crazy metrics and blah, blah, blah. But that that hasn't happened. We've tried that as a movement for as long, at least the 50 years I've been alive and longer. Not very far. So that's where I'm at.
That was a beautiful answer, Tim.
It's a very long answer. Sorry, folks.
Very good. Are you good with having 2 more questions?
I'm great with it. Yeah, I'm comfortable.
I think you hand up forward.
So I hear on the one hand, you're going to be sort of a market tipping point story with the electric cars, right? Which on the one hand, and I think some of the discussions we've been having is, so this is a way to circumvent industry captured governments that are, captured by the status quo, resisting this environmental benefits. The other hand, I just read this great book by Jean-Baptiste Clairaut.
More and more. Yeah. So
and that opened my eyes to a lot of things that I had been resisting previously. One, obviously, the sort of degrowth conclusion that we cannot keep on consuming more energy, or Dyson spheres are not in our near future.
Exactly.
And that this transition to renewables, as there was a very important report, Franco's et al. Talking about if we have small cars, there's enough lithium to go around. If we have Hummers, 1,200 horsepower Hummers, there's not going to be enough lithium. And so there's this question of not just, sort of saying the Norwegian example where have come through because they're being sold as, more car, this same sort of toxic masculinity car culture.
Yeah.
There's these other, so that's like the setup. And then my question has to do with backlash, right? Because we see from, I'm thinking DDT, when we phased out, because agriculture obviously is a huge part of climate. And when we phased out certain pesticides, they had 10 more that came online, and some of them were worse than the originals. We call it for regrettable substitution in the chemical industry. And I'm wondering what sort of regrettable substitutions have been taken into account in some of these models that you've been working on.
Yeah, great question. So probably should say off the bat, I hope I'm clear. I'm not saying electrifying personal mobility is the answer to everything. Far from it, and there are some caveats in there. At the same time, I'm far more excited about the electric two-wheelers and three-wheelers in the majority world than I am about the cars, for what it's worth. But they pivot off the same core technology. I will advocate for cheap batteries and a new generation of them that will be coming, and then another generation. We looked specifically at the numbers for all the major elements, by the way, with JF and Femke. We've gone into this in some detail, and the data we have and the analysis we have, there is not a problem of shortage. There is no fundamental, there isn't enough lithium or cobalt or you name it. However, the price is a different question. But yeah, your core question is, you can't just think ultimately about substitution. It goes back to the earlier question. We ultimately have to have deeper changes, some of which are arguably underway without us noticing, as I hinted. But at the same time, I am a sort of pragmatist at the level where I say, are people going to continue to want some personal mobility in their lives? You're all here. I suspect you travel different amounts of distance to get here, but you made a choice that you wanted to have the ability to come here. And I conclude we will want to be able to move around, and it's not, in my version of, okay, we may rightly, it'd be good if some people who'd had far too much personal mobility and far too gratuitous did less, and that norms changed in a way that was somehow policed. But I still think there's some core things we'll want to do as people to have flourishing societies that won't go away completely. And we should do those in the least harmful way to the planet, which comes back to your question of, well, is your proposal that you're focusing on here, Tim, less harmful, etc.? Well, yeah, that should always be asked, and there should always be application of the precautionary principle with new technology, and there should always be the quest from innovation towards less harmful solutions to meeting our kind of core. They're not just needs, are they? You could classify mobility as more of a, I don't know if you can call it a desire, but I think it's still a legitimate one for a good life. So yeah, I love the question. I don't think the technologies we have at our disposal are the ultimately best ones, and we should always be careful not to introduce new harms. But we should also fully be behind the innovation to come up with better and better options for me. That's a personal view that means that we need a culture that still rewards entrepreneurship and innovation to a degree, which is maybe a difficult pill to swallow, because arguably that's at the core of what was the Industrial Revolution and the new Green Industrial Revolution. So that feels a bit uncomfortable. But if we didn't have, and if some people weren't incentivized to entrepreneurially innovate, I think we're going to have that, and we're going to have to live with some of those tensions. But I'm happy with people to take a different position. Yeah, very good, really good.
Just a super small follow-up. Would you say that it would be, say, in the sense of green innovation, we know that, for example, in the Ruhrgebiet in Germany, with all the coal mining, which is all mechanized now with these huge machines, that the actual health harms to the workers is much less than, say, 200 years ago when they were digging it out, right? So I would say that that's a good thing, even though that the machines give us tremendous levers to extract more than we ever have. So I guess the equivalency, because we've seen, I hope we've all seen, you see the lithium mines and all the electric battery mining is teeny compared to coal mines.
Yes.
So would, from an equity environmental justice perspective, sort of getting better mechanized extraction of these rare earth minerals or logical intervention, so we have to have less slavery and less exposure for these people?
Possibly, yeah. That's all part of that scales of doing a proper job on scales of justice, avoiding creating any unnecessary harms and trying to minimize total harm. And I think that I might be going, I just invite a collective activity on doing those scales of justice in this rounded way that we're talking about. I just find that I get a little dismayed when you get the inevitable question, what about the mind? Because we're so prone to losing sight of the systems picture here. And I just, if I haven't made it clear already, you absolutely got to think when you're talking about these issues of harm, we've really got to see the whole picture and seek to minimize it.
That's a great note to end on.